Welcome back to Low-Level Programming Crashcasts. I'm Sheila, and I'm here with Victor to dive into another fascinating topic in computer architecture. Before we begin, I'd like to remind our listeners to rate our podcast on your favorite platform. Your feedback helps us improve and reach more tech enthusiasts like you.
That's right, Sheila. And today we're continuing our journey through the Understanding Computer Architecture chapter. We've already covered the basics of computer organization and CPU components. Now we're moving on to a crucial aspect of computer architecture, the memory hierarchy.
Ooh, that sounds intriguing. But before we dive in, I have a quiz question for our listeners. Here goes. What's the typical access time difference between the fastest and slowest levels of the memory hierarchy? Is it about 10 times, 100 times, or 1 million times? Or,
That's an excellent question, Sheila. It really highlights the vast differences in speed within a computer system. Listeners, take a moment to think about it. Consider the various storage types you're familiar with, from the lightning-fast CPU registers to the comparatively sluggish hard drives. The answer might surprise you.
now let's start with the basics. Victor, could you explain what we mean by memory hierarchy in computer architecture?
Certainly. The memory hierarchy is a structural design concept in computer architecture that organizes different types of memory based on their speed, capacity, and cost. It's like a pyramid, with the fastest but smallest and most expensive memory at the top, and the slowest but largest and cheapest memory at the bottom.
I see. So it's kind of like how we organize information in real life, like how we keep our most important notes close at hand, less critical info in a drawer, and rarely use documents in storage.
That's a great analogy, Sheila. In fact, we can take it a step further and compare it to a library system. Imagine you're a librarian. The books you're currently reading are like CPU registers, immediately accessible. The books on your desk are like cache memory, quick to access but limited in number. The bookshelves in your office are main memory or RAM, while the vast library archives in the basement represent secondary storage like hard drives.
Oh, that makes it so much clearer. So can you break down the levels of this hierarchy for us?
Absolutely. Starting from the top, we have Point 1. CPU registers, the fastest but very limited in capacity. 2. Cache memory, usually divided into levels, L1, L2, L3, faster than main memory but smaller. 3. Main memory, RAM, larger capacity but slower than cache. 4. Secondary storage, hard drives, SSDs, the largest but slowest.
I've always wondered, why do we need this hierarchy? Couldn't we just use one super-fast large memory?
Great question. It all comes down to a balance of speed, cost, and capacity. Fast memory is expensive and can't be made in large capacities, while large, cheap memory is slow. The hierarchy allows us to have the best of both worlds, the speed of small, fast memory and the capacity of large, slow memory.
That makes sense. So how does the computer decide what data goes where in this hierarchy?
That's where the principle of locality comes in. There are two types: temporal locality, which means if a piece of data is used, it's likely to be used again soon, and spatial locality, which means if one memory location is accessed, nearby locations are likely to be accessed soon too.
Oh, I think I get it. So it's like how when I'm cooking, I keep the ingredients I use most often closer to me on the counter and less frequently used items in the pantry.
Exactly. And just like in cooking, this organization significantly speeds up the process. Now let's talk about one of the most important components of the memory hierarchy: cache memory.
Ah, yes, I've heard of cache. It's super fast, right? But how does it actually work?
Indeed, it's very fast. Cache works on the principle of bringing copies of data from slower, larger memory into smaller, faster memory. When the CPU needs data, it first checks the cache. If the data is there, it's a cache hit, and the CPU can quickly access it. If not, it's a cache miss, and the CPU has to fetch the data from slower memory.
That's fascinating. But wait, if we're copying data around, how do we ensure everything stays consistent?
That's an excellent point, Sheila. This is where cache coherence protocols come into play. These are mechanisms that ensure all copies of data across different caches remain consistent. It's a complex topic, but essentially, when data is modified in one cache, the system ensures that all other caches with that data are updated or invalidated.
Wow, there's so much going on behind the scenes. Now, I've also heard the term virtual memory. How does that fit into all this?
Virtual memory is a memory management technique that uses both hardware and software. It creates an illusion of a very large main memory by using secondary storage to extend the physical main memory. This allows running processes that require more memory than physically available in the RAM.
That's incredible. It's like the computer is playing a clever trick to make itself seem more capable than it physically is. But how does the computer keep track of what's where?
That's where the Memory Management Unit, MMU, comes in. It's a hardware component that translates virtual memory addresses to physical addresses. It maintains a page table that keeps track of which virtual pages are currently in physical memory and which are on disk.
This is all so intricate. I'm starting to see why memory hierarchy is so crucial to a computer's performance. Before we wrap up, could you share a common misconception about memory that our listeners should be aware of?
Certainly. One common misconception is that RAM and storage, like hard drives or SSDs, are the same thing. While both store data, RAM is volatile and much faster, used for active processes, while storage is non-volatile and used for long-term data retention.
Thank you, Victor. This has been incredibly enlightening. Now let's reveal the answer to our quiz question. The typical access time difference between the fastest and slowest levels of the memory hierarchy is actually about 1 million times. Isn't that mind-blowing?
It really is. And it underscores why the memory hierarchy is so important in modern computer design.
Absolutely. To sum up today's episode, we've learned that the memory hierarchy is a crucial concept in computer architecture, organizing memory from fast and small to slow and large. We covered CPU registers, cache memory, main memory, and secondary storage, and how principles like locality and virtual memory help optimize performance. Remember, understanding these concepts is key to grasping how modern computers achieve their incredible speed and efficiency.
That's a great summary, Sheila. And to our listeners, we hope you found this deep dive into memory hierarchy enlightening. Remember, if you enjoyed this episode, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us create more content like this.
Absolutely. And don't forget to subscribe to the podcast and rate us on your listening platform. We truly appreciate your support. Until next time, keep exploring the fascinating world of low-level programming.